Welcome to the module Cam Synthesis. The cam and follower mechanism is one of the widely used mechanisms in engineering applications. In this module, you will learn how to use the motion of a follower to create a cam profile. Along with that, you will learn about the trace path command, which allows you to graphically display the path that any point on a moving part follows. In this module, you will learn how to use the data points to drive the motor. You will also learn how to interpolate the data points using spline. Then, you will learn how to create a trace path of a point to get the cam profile and a SolidWorks part using the cam profile. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. The cam and follower mechanism is used in internal combustion engines to operate the inlet and the exhaust valves. In this module, we will generate a cam profile based on a dataset. The dataset used for this is an input follower displacement. In SolidWorks Motion, trace path allows us to graphically display the path that any point on a moving part follows. For example, let's look at the 4-bar linkage mechanism. We can see the trace path of nodes of the green link. We can select the part that will be used to generate the trace curve by selecting it in the Select Trace Point component field. Similarly, this field also enables us to select a face, edge, or a vertex to define a point generating the cam profile. The option Show Vector in the Graphics window is used to view the trace path generated in the graphics area. Note that the default reference frame is the global reference frame defined by the global coordinate system. Let's see how to create a trace path, which will define the cam profile. Click Show Me to launch a demonstration video. The Cam Synthesis assembly file has been opened. We can see that the assembly consists of an undefined cam and a follower. We will start by setting up a motion analysis. In the motion analysis, the cam part, shown in orange, will spin 360 degrees. At the same time, the follower, shown in blue, will move up and down. The desired movement of the follower is known and will be driven by data in a spreadsheet. Once the motion analysis has been run, a trace path will be created showing the relative movement of the follower with respect to the movement of the cam. The trace path will be used to create the cam's profile. Verify that the document units are set to millimeters, grams, seconds. Right-click Motion Study 1, and then click Rename. Enter Cam Study as the new name of the motion study. Set Motion Analysis as the type of study in Motion Manager. Now, we will add a rotary motor to drive the camshaft at a constant speed of 20 RPM. This will rotate the cam once in every 3 seconds. Click Motor. Ensure that rotary motor is selected. Next, click the face of the camshaft. For motion type, ensure that constant speed is selected. Next, to set the speed, enter 20 RPM. Click OK. Now, we will add a linear motor to the top face of the follower. Click Motor. Then, click Linear Motor. Select the top face of the follower. Notice that the motor is acting upward. We will need to ensure that the motor is acting in the downward direction by clicking Reverse Direction. Now, the direction of the motor is reversed. Click the drop-down arrow and click Data Points. In this situation, the vertical movement of the follower is known. The option Data Points is selected because we have a spreadsheet relating displacement to time. This opens the Function Builder dialog. Now, to set value, y, click the drop-down arrow and click Displacement. Ensure that time is selected for independent variable, x. In order to calculate the displacement between the data points, an interpolation method must be used. There are 3 interpolation options available: linear, cubic spline, and Akima spline. A linear interpolation will draw a straight line between the data points, while a spline will create a curvature continuous path through the data points. Generally speaking, a cubic spline will over-exaggerate the curve through the data points. Therefore, we will use the Akima spline interpolation. Click Akima spline for interpolation type. Click Import Data. Open the Cam Synthesis file. This file contains a table relating the displacement to time. Click Open. Now, click OK to close the Function Builder window. Click OK again to close the definition of the linear motor. Gravity in the negative y direction has been added. Now, we will change the study properties to save 100 frames per second. Click Motion Study Properties. Next, change the frames per second to 100 and then click OK. We have set the assembly key to 3 seconds. Click Calculate. Now, we will create a trace path, which will define the cam profile. Click Results and Plots. Select Displacement, Velocity, Acceleration as category and Trace Path as subcategory. The cam profile is defined by the relative motion of the follower to the cam wheel. Therefore, select the vertex on the follower to define the cam profile. And then select the surface of the cam to define the reference component. Leave Component to define XYZ directions empty. Click OK. Note that a cam profile is generated. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a trace path which will define the cam profile. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. The trace path curve can be used to create a curve in a SolidWorks part to create geometry. There are two ways to do this. The path can be used to create a curve in an existing or reference part, or it can be used to create a curve in an entirely new part. If the part exists, then using the first way, the trace path curve can be imported to the existing part. If a part has not been created, then using the second way, it can be done directly. Let's see how to export the trace path curve to a SolidWorks part. Click Show Me to launch a demonstration video. Scroll down in the Motion Manager tree. Expand the Results folder. Right-click Plot 1. Click Create Curve from Trace Path. In this case, we will create a curve which will be added to the cam part. Therefore, click Create Curve from Path in Reference Part. Scroll down in the Feature Manager design tree. Click the cam. Click Open to open the cam part in its own window. We can see that the curve has been inserted into the part as a suppressed new feature. We will start by unsuppressing the curve. Then we will create a sketch and copy the curve to the sketch using the Convert Entities command. Finally, an extrusion will be made from the sketch. Click Curve 1 and click Unsuppress. Click the Sketch tab. Click Sketch. Expand the Flyout Feature Manager design tree. Click Front. Click Convert Entities. For the Entities to Convert selection box, select Curve 1 and the outer cylindrical edge of the cam profile. Then, click OK. Click the Features tab. Click Extruded Boss Base. Under Boss Extrude Property Manager, for Direction 1, click the drop-down arrow and click Mid-Plane. For depth, enter 50 millimeters. Clear Merge Result. Click OK. Click Save to save the changes. Click Close to close the part file. Click Yes to rebuild the assembly. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about exporting the trace path curve to a SolidWorks part. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Let's see how to examine the motion of the cam profile and plot the vertical displacement of the follower. Click Show Me to launch a demonstration video. Now, we will create solid body contact between the follower and the cam. We will also disable the linear motor currently driving the movement of the follower so that the follower is only driven by contact with the cam. Click Contact. Ensure that Solid Bodies is selected as the contact type. Next, we will click Follower and Cam as the solid bodies. To do so, first, click Follower. And then click Cam. Next, we will specify the material. To do so, under Material, click the drop-down arrow and click Steel, Greasy. Similarly, select Steel, Greasy as the material for cam. Clear Friction. Click OK. Before moving ahead, we need to disable the Linear Motor 1. Right-click Linear Motor 1 and then click Suppress. Next, click Motion Study Properties. Ensure that checkbox for Precise Contact is selected. Click OK. Now, we will click Calculate. Notice that the follower is not touching the cam. This separation is the result of the momentum of the follower. Just prior to this time, the follower was driven up by the cam. The cam profile requires the follower to change direction rapidly. However, the only thing holding the follower in contact is gravity. Probably, this will not be a problem since the follower will eventually have additional components on top of it to force contact with the cam. Now, we will create a displacement plot of the center of mass position of the follower in the y direction. This plot will be compared to the displacement seen in the spreadsheet. Click Results and Plots. Select Displacement, Velocity, Acceleration for category, Center of Mass Position for subcategory, and Y component for result component. Next, click Follower. Then, click OK. Notice how the vertical displacement of the follower is plotted. This profile should be the same as the one seen in the spreadsheet. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about examining the motion of the cam profile and plotting the vertical displacement of the follower. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. The plot for the vertical displacement of the follower was created in the previous Show Me. Now, we will compare this plot with the plot of the profile data. For clarity, the profile data has been inverted. Both plots have the same shape. The plot of vertical displacement of the follower shows that the maximum displacement is 116 millimeters, 1053 minus 937, and the plot of the profile data shows that the maximum displacement is 116.24 millimeters. On examining these two plots, we can ensure that the CAM profile created is in agreement with the input profile data. Here's a question to check your understanding of what has been covered so far. In machine design, the independent variable, time, is often not the most convenient choice. It may be more comfortable to design all tasks in terms of one master cycle. Typically, the duration of one master cycle is set to 360 degrees. Cycle-based motion allows the user to easily modify the duration of the cycle. To have cycle-based motion, first you need to set the independent variable to cycle angle in Function Builder. The duration of the cycle is then specified in Motion Study Properties. Let's see how to set cycle angle as the independent variable and analyze the results. Click Show Me to launch a demonstration video. Now, we will change the motion type of the existing rotary motor to segments. To do that, right-click Rotary Motor 1. And then click Edit Feature. Under Motion, click the drop-down arrow and click Segments to open Function Builder. In Function Builder, make sure that Segments is selected. Keep Displacement for value, y, and set the independent variable x to cycle angle. Add a row by clicking Click to add row. Retain the value for start x as 0 degree. Enter 360 degrees cycle angle for end x. Enter 360 for the final value of the rotational displacement. Set the segment type to linear, default. The four graphs indicate the linear increase of the displacement, constant velocity, zero acceleration, and jerk. The 360-degree rotation in the 360-degree cycle angle indicates 1 revolution per output cycle. Click OK to close Function Builder. Next, click OK to save the new definition of the motor. Now, we will set the duration of the output cycle. Click Motion Study Properties. And then click Cycle Time. Set the cycle time to 3 seconds. Click OK. Then click Calculate. Notice that the resulting motion of the follower is the same as it was in the previous Show Me. This is expected as the simulations are identical. The former was solved using time as an independent variable, and the latter one using cycle angle as an independent variable. Now, we will adjust the cycle time to 1.5 seconds. Click Motion Study Properties. Set cycle time to 1.5 seconds. Click OK. Click Calculate. Notice the cam now rotates twice in 3 seconds. However, when reviewing the trace path, we see that the follower detaches from the cam, which is unacceptable. The cycle time of 1.5 seconds is, therefore, too small for this mechanism. Finally, click Save to save the file. Now, click Close. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about setting cycle angle as the independent variable and analyzing the results. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module, Cam Synthesis. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt this exercise, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the eCourse details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the eCourse.